Hi class, we are on section 16.3. This is the equilibrium constant. So the equilibrium, as we've discussed before, is when the forward reaction rate is equal to the reverse reaction rate, and it's expressed in terms of concentration of the reactants. However, it's in terms of the concentration of reactants and products at the equilibrium, not at the initial. So we need an equilibrium constant, a numerical value that will help us understand where the reaction lies. Does it lie towards the products? Does it lie towards the reactants? Or is it equal in amounts of both? So here's a general expression. And the equilibrium constant expression is with the products on top, the reactants on bottom. So if you have to think of this as a ratio. And the coefficients are the powers raised to that concentration of that either the reaction or product. So you can see the A's, the B, C, and D. So it's the coefficients, we raise them up. So a few things here. Always products over reactants, so products over reactants. Plug in numbers and that will give you the rate, equilibrium rate constant. The lowercase letters represent the coefficients of the balanced chemical equation. So regardless of the initial concentrations, we're not concerned about initial concentrations when we're dealing with equilibrium. We're interested in the concentrations at equilibrium. So the ratio of concentrations raised to appropriate powers will always equal the same value. This is the equilibrium constant is unitless, and this is known as the law of mass action. I'm not going to go too much in the law of mass action, but you should know what it is, which is exactly what we're looking at here. So when it's referred to, this is what it is, the law of mass action. And here's some more general, I found a slide of just some general information, but the definition is a mathematical expression holds that for a reversible reaction at equilibrium and at constant temperature, a certain ratio of reactant and product concentrations has a constant value of K, which is the equilibrium constant. So the value of K depends on the specific chemical equation and on the temperature. The value of K is not dependent on concentrations, particle size, or catalysts. And the equilibrium constant does not include solids or pure liquids. That's because, think of a solid, if you remember back in Intro to Chemistry, the solids, the atoms, molecules, particles, whatever you want to call them, they're stuck in place. They can't move anywhere. So there's only vibration. So there's not a reaction going on with this. And pure liquids, they're just pure, so neither of these can we get the concentrations for. So it's only aqueous and gaseous, even if you have a solid or pure liquid in a reaction. Okay, so according to the law of mass action, what is the correct expression for the equilibrium constant? So if we look at this here, the easiest way to do it is look at one of the reactants or one of the products. Since we only have one reactant, that's what I'm going to look at. I know this has to be on top, so I'm going to look at all of these. And the one that I can instantly kick out is C, because it doesn't match. Now it has a coefficient of 3. Now that's going to be raised to a power. So I know that I'm going to look and see if I can find a 3. This has a 3, but it's on the outside. So I'm going to kick this one out because it's not in the correct format. So I'm looking, so B and C are now gone. A doesn't have a 3, so the only one left is D, and it's raised to a power of 3. So let's check. A is on the bottom, and it has a raised to a power of 2, and there's B. So D is the correct answer of how to set this up. And then if we look at an actual reaction, I'm going to look at the reactant. So let's take a look and make sure that it has one reactant at the bottom, raise the coefficient to 2. Because these are all gases, all of them should be here. So we have 3 compounds, and we should have 3 compounds on the equilibrium constant. We have oxygen, which is a 1, and then we have a 4, and the 4 is raised up. So this matches exactly the reaction here. Okay, so write an equilibrium constant expression for, and we have silver sulfide, and it decomposes to the ions of silver and sulfide. So here we go. If we look at this, though, do you notice the first thing is the reactant is a solid. This cannot be part of the equilibrium constant. So the only thing we're going to write up for is the reactant, the products. The reactant's not going to be held in this. Now the bottom one has liquid in it, and which is water, pure liquid. We also do not count that. So we're going to kick that out when we write the equilibrium constant expression. So we're going to have, even though we have 3 compounds, we're only going to consider 2 in writing the equilibrium constant. Okay, so this isn't in your book, but I just want to explain where the K comes from. So we have a forward reaction of iodide, and it ends up decomposing or coming together, however you want to say it, producing Sorry, my mind went blank for a second. So we're looking at gaseous iodine at high temperatures, and what it takes to combine to form a diatomic iodine. And so this is our forward reaction rate, so we have a rate constant for that. And this should be a subscript up here, so I apologize for that. Then if we look here, I noticed I did it on all of them. This should be a superscript, so it should be up here. This should be a superscript. Sorry about that. Of course, I notice always after I'm done, it looks like I didn't catch this page at all. Okay, so then the reverse reaction is the inverse of the forward one. So when we write the rate of reverse, it's going to be the inverse. So 1 over the reaction of the forward reaction. And at equilibrium, the rates are equal. So we can set them equal to each other, which is when we plug it in here. And I still didn't catch it. But what we do is we can rearrange this to with the constants on one side. And we can move the ratio of rate constants. So this is the ratio of rate constants. We have our concentrations on this side. And what you see as this is equal to the equilibrium constant. So if we could like remove this part, you can see that setting this up as a ratio is equal to the equilibrium constant. That stands for K. And you can see here, if we look at concentration over time, you can see that the reactant is going down, which was what we expect, and the product is being produced, which is what we expect. But if we look at it in a different way of rate over time, we will see that they will eventually meet in the middle somewhere on this graph, and that will be the equilibrium because it's continuously going. All right, so what does K represent? K represents the equilibrium constant, and it tells you which the conditions are more favorable at equilibrium. So if you have a large K, that means more than the number 1, then that means that you're going to have mostly products, and depending on how big that number is, you'll have more products than reactants at equilibrium. If we have a small number, which is less than 1, that's when you start getting the exponents of negative something. Like 4 times 10 to the negative 5. If it's a negative, you see that negative, it's a small number. That means that more products, more reactants are going to be produced than products at equilibrium. So if we look at here, the value of K is the equilibrium constant, and it gives quantitative information about the extent of the reaction. So if the forward and reverse reactions, if you have a K that's approximately 1, that means the equilibrium is approximately 1, then that forward and reverse reactions are equally favored. If you have a K that's over 1, then that means that the products are favored over the reactants, and you'll have more products than reactants at equilibrium. And if you have a K that's less than 1, it's the opposite. You'll have a reverse reactions favored, and you'll have more concentration of reactants over product. So if we have a number, you should easily be able to tell somewhat what's going on. So if reaction of A produces B in equilibrium reaction, we have K equals 1.5 times 10 to the negative 5. Is there more A or B at equilibrium? Well, we just covered what one is the base. The one is what we go stand by and determine if it's on one side of 1 or the other side of 1. Since this is a negative 5, that means that this is less than 1. So that means it's a small K, and the reverse reaction is favored. So you're going to have more A than B at equilibrium. Okay, so now we're going to get into manipulating equilibrium constants. We are going to try to, if we need to find out an actual value, we can manipulate equilibrium constants to determine our numerical value. So for instance, in this case, when a chemical equation is manipulated though, everything has to change. So if there's any change to something, everything has to change on it because it will affect the rate constant, it will affect the concentrations, it will affect everything. So for instance on here, reversing the equation yields the inverse equilibrium. So if we have an A produces B here, so we set that up, here's our equilibrium constant. Well, what if we reverse that reaction? So here is it being reversed. So in order for us to still use the equilibrium constant, we actually have to do 1 over K. So it's the inverse of the equilibrium constant for the forward reaction. So you see these are flipped, and that's where you do the 1 over K. And K in this prime here, that means K reverse. So this is K reverse, and right here would say K forward. I have some examples to show you of these. If 2 or more equations are added together, so you need to know a numeral value, a value for an equilibrium constant. you could use other equilibrium reactions in order to determine it. So if two or more equations are added together, the equilibrium constant for the overall reaction is the product of the individual equations. So we did something very similar. You should have done something very similar to this in Chem 111, where you would add everything up, and you, especially for the standard heat of formation, you would add everything, you would remove stuff, you would multiply, you would divide, you would do everything in order to get to the reaction that you wanted, thereby understanding the enthalpy of it. So, or the heat of formation, standard heat of formation. So here we have two moles of A produces B. So we set that up, and remember we raise the power of the coefficient, and now we have plus B produces C. So we also have that one. If you set them up toward with each other, you can bring everything down. That doesn't cancel out. In this case, B is the product for this portion, and it's in the reactant of this, but they cancel out because it's B minus B. And so the overall of what this is 2 moles of A produces C. Well, we also have to do something to the rate constants. So for the overall, we have to multiply them together. So here is B over A. So this one here is K1. Over here is K2, and even here you can see what you can cross out, and that gives us the overall of the equilibrium constant. And if you had numbers, you would plug these numbers in. Okay, so here's an example. We have a reaction here that we have a rate constant that gives us an actual value, though we're not really haven't worked with values yet. I'm going to give you with values so you can actually see the steps. We have a second reaction here and another rate value, a rate constant. Now, it's telling us to sum these two equations up, and it'll give us a final overall reaction. So we do that, and if you set them up, what you notice is that we have Br2 here and Br2 here. We can cancel those out, but there is nothing else to cancel. So we're going to bring everything else down. Now, what you need to do is that you have a new overall equilibrium constant. So you need to set, if you can visually set this up, or you can go straight to the next portion if you understood what was happening here. So here we have K1. So you see we have the all, if you look at it, you have all the products on one side, and you have all the reactants down below, except for what was crossed out. Now what it means is that you can multiply these together if you just set them in this form here. So that's what you're seeing. You have this form here, and you have this form here, and you can still see what needs to be crossed out. So by K1 and K2, if you multiply these together, though, you'll actually get a value. You'll know what this reaction is, and you'll get the rate constant for that reaction. Okay, so this problem here has a mixture of everything that I just discussed. So one thing I want to point out, we have one more manipulating equilibrium constant, and I'm going to show it to you in the problem that's previous. So when coefficients of a reaction are multiplied, you have to also multiply the rate constant, equilibrium rate constant, and raise that power. So here's a perfect example. We have A produces B, so we set up that rate law constant, equilibrium rate law constant. And now, what if we multiplied everything by 2? So if we multiply, we have 2A produces 2B. Well, we also have to put in that for the rate law constant. So what we do here is, remember, you raise the coefficients up to the power. So we have 2 here, a 2 here, but we also have to put a 2 here. What if we divided everything by 2? Then we would also have to raise this power up by the coefficients. So that's what you see here is a half and a half and a half. So we're actually doing this problem. We have everything in this problem here. So we have 2 reactions, and we want this reaction that's in bold. And we're going to have to manipulate these in order to get this reaction. We also have rate law constants for these. So the first thing you do, and this is the 1, so when I say 1 here, this is exactly what we've done here. We multiply everything by 2 because we have this reaction here, but see it's 2HF. So we're going to multiply everything by 2. When we do that, we also have to raise it in the powers. So that's where you see the K2 right there, because there's a 2. So that's what you see here. So that gives us a new equilibrium rate law constant, and it's 4.6 times 10 to the negative 7. Now the second one, we need to reverse the second equation because we have the ions on this side here, which is what we need, and we need to have the product, which it would be here, this on the other side, because if you see that's right there. Oops, there I go. So we reverse that, and when we reverse it, we have to do the inverse of the rate law constant. So this is the forward reaction. We're going to do it as a reverse, and we have to take the inverse of it. And that is where you see this right here. It would be this one, which is explaining reversing it. You have to use it 1 over k. So now we have a new rate law constant for the reverse reaction. We can add these together. And when we add them together, we can see what cancels out. And then we can give the final balanced equation. And multiplying these together also gives us a value. So this slide here has all three. It gives examples of everything. It's a little complicated, but not overly. And this definitely, hopefully in 111, you worked on something very similar in a different section. Okay, so we covered that. So reversing the equation yields the inverse equilibrium constant. If two or more equations are added together, the equilibrium constant for the overall is the product of the individual equations. When the coefficients of a reaction are multiplied by a factor, then the equilibrium constant has to also be raised to that power of that same of what everything was multiplied by. Okay, that's it.